All right, it's being recorded now. So good afternoon, everyone, and welcome to lecture number 20 of this course, Continuum Mechanics. So we are almost halfway through the course now, and making good progress now, especially because of this online teaching. It's a bit faster than as we expected because there's nothing to slow me down. I only see 4 of you today here, which is all right because the video is being recorded, so the others can access it through YouTube or Moodle. So let's continue. So we've been talking about kinematics in the last 2 lectures. So we talked about how to quantify the motion, and we towards the end of the last class we talked about material derivative. And so today what we'll do is we will start with material derivative again briefly, and then I will give you a mathematical proof of the point where we stopped last time. So let's give a quick recap of material derivatives is. So we said that it's material derivative is nothing but the time rate change of a property. Okay, so with that we denoted using theta. This time we'll call it P. So we have the time rate change of a property P, which could be a tensor. So let us say it's a second order tensor. But it could be any nth order tensor. In this case, we also said that we sometimes denote the material derivative as capital D by capital dt of Pij, and we also call this as the total derivative. I'll tell you why we call it the total derivative in a couple of minutes. So first, the intuitive understanding of what this means. So P is a property. Let us say P is a physical property that we are measuring, and d by dt of P means that you take a probe that you're using to measure the property change. You sit on a particle. Hypothetically, you sit on a particle. So let's say there's a body that's deforming. So there's a motion which is causing the particles to move in space. So what you do is you sit on a particle P. Well, let's call it particle Q. So particle Q, you sit on it, and then you measure the change of the property Pij with time. So the rate of change of that property that you measure by sitting on a material particle is called material derivative. Okay, so the word material comes from the fact that you are sitting on a particle, and remember that in material reference system or material coordinates, you denote, these coordinates are fixed to particles because they are fixed at t equal to 0. So given any material coordinate I, x1, x2, x3, that denotes some particle P. Okay. So we can write this material derivative of P. Let us say P is given in the material or the Lagrangian coordinate system. So we specify P. So we specify this in terms of capital X and T. So capital X here denotes the material or the Lagrangian coordinate system. So if that is the case, then this is nothing but dou by dou T of Pij capital X comma T. And it's easy to understand here because capital X has, the partial derivative of capital X with respect to time is 0 because capital X has no dependence on time. So the d by dt here is the same as dou by dou T. So I'm writing here again that we call it the material derivative because the time rate of change of Pij in this case is measured for some material particle. And you can see that here because you have an x given to you. So if I supply some particular value of this capital X, so let's say I have some body in the reference coordinate system. So you have a point Q here, and the point Q has capital XQ as its material coordinates. So as I move along through different deformations, what I'll see is that the capital X or the material coordinates of particle Q will not change. Because remember that material coordinates refer to where the particle was at t equal to 0 in the reference coordinate system. Okay. So this capital Q's material coordinates will not change. So if I supply some value of capital X here, that basically means that I'm talking about the rate of change of P for some particle at some later time t. So a particular value refers to a particular material particle. Now, of course, I mean, you may specify that here, but analytically, you may actually write your d by dt as a mathematical function of capital X and t. So what that will basically tell you is, it will tell you the rate of change of the material derivative as a field. So you put any particular value of capital X here, and that will give you the material derivative value for that particular material particle. Okay, so this is the intuitive and the mathematical meaning of material derivative. Now, many people get confused as to what's the motivation behind having something called a material derivative. Now, the motivation is because when we write Newton's laws of motion, which are equally valid for in quantum mechanics, when writing Newton's laws, we will have to have some collection of particles, and we will say that the net external force acting on this collection of particles is equal to net external force is equal to the mass of these particles times the acceleration. Yeah, that's what we do when we write Newton's second law for this collection of particles. So when we have a collection of particles which may be in motion, okay, let's take fluids which are in motion or solids which are going through deformation. So in that process, we will want to write this for a collection of particles, not a control volume or a volume which is fixed in space, because Newton's law is valid for some mass m. So if I take a collection of particles which has a mass m, then I write the Newton's second law of motion for those particles. So if the particles are moving, then to write this acceleration, I may want to have a material derivative, which simply tells us that it's the rate of change of the property of certain particle, or I mean, you can integrate over the particles in space and you can get the complete body there. So we particularly write the material derivative to write the Newton's second law, which we'll be doing later. But that's the motivation behind understanding or learning about material derivative. So it's the rate of change of some property P for a given particle or given material particle. So the particle may be moving. So you sit on the particle and measure the rate of change of P. And then later we said that in many situations it's more intuitive to describe the property P in the spatial coordinates. All right, so it will be very intuitive to write the property Pij in the spatial coordinate system that is using the Eulerian description, that is small x. Okay, so the small x coordinate system, if you remember, is fixed to your room or space rather than being fixed to some particular time. So that means that if I specify some coordinates in the room coordinate system and I specify some time, then you would want to know the material derivative at that particular point in space at that particular time. Okay, so again, the intuitive meaning of material derivative stays as it is. It's just that mathematically we try to understand how to write that when P is described using Eulerian description or the spatial coordinate system. So we write this as d by dt of Pij, which is a function of small x and t. So when we apply the chain rule of differentiation, so since P is a property of small x and t, so we may write this as the partial derivative of Pij as a function of small x and t. And then since you have a small x as well, and you know that the partial derivative of small x with respect to t is not zero, so small x is a function of time. So then we write this as del by del xk Okay, so this is something that we discussed in the last class. So this is written using chain rule. So this first part, which is the partial derivative of the spatial description of P with respect to time, is called the local rate of change. Okay, so it's called local for the reason that you are calculating the partial derivative of P with respect to T for a given small x, that is for a given position in your room or for a given local position. So locality refers to staying constrained at point small x. So you're calculating this derivative with respect to small time at a particular position or a particular point in space. And the second term, which involves your dxk by dt, that's nothing but your velocity, is called the convective rate of change. All right. So we also tend to write, we can simply write this, the material derivative for the Eulerian description as, so d by dt of something is equal to dou by dou t of that thing plus v dot grad of that thing. Let's write that as Pij here. So you can see that dou by dou xk of Pij is nothing but the gradient of Pij, and dxk by dt is nothing but your velocity. And since you have the index x here, that since the Einstein notation is applied here, so that basically means there's a dot product here. So this is how you write the material derivative in for a quantity which is described using spatial coordinate system or the Eulerian description. Now, to have some intuitive understanding of the material derivative, I can give you an example. So let's think of the first term. So we will try to understand these two terms independently. So let's think of a situation where your second term is zero. Okay, so the easiest one to think of is where your velocity v or the velocity field at all the points is zero. So let's look at a situation where you have a swimming pool. it's a swimming pool, which is nothing like a tank. You have water in it, and you take a point P, a point, what you can call the point as P inside it, and you try to measure the temperature by putting a probe. And remember that there's no velocity field, so that means there is no movement of water. So the water is completely stationary. It's a hydrostatic situation. So you put a probe at point P, where the point P is somewhere inside the pool, and the pool's full of water. So you try to measure the temperature theta at some particular space location and T, and you try to measure the rate of change of that. Now, since there's no motion, so the only way you can see an increase or decrease in temperature is where, so let's think of a situation where you have, it's a sunny day, so you have sun, which is radiatively heating the pool. So what you see is that the temperature at a given point P starts increasing. Okay, it can definitely happen. It's a cold pool and the sun comes up, so it starts heating the water. But there's no movement of water. Let's assume that there's no convection current, there's no movement, there's no flow of water in the pool. It's completely stationary. Theoretically, well, hypothetically, let's assume that. So the only rate of change that we will see is because of the radiative heating at a given local point P. So that is what tells us that that's equivalent to the dou by dou T of Pij, or in this case, Pij is theta, the temperature. Okay. So the overall rate of change that you may measure by sitting on a particle is the rate of change, which is the local rate of change here because of the radiative heating of sun. So you are actually, I mean, since there's no motion of any particle, so these two are equal. Okay, so that's a situation where convective rate of change is 0, and the local rate of change contributes completely to the material derivative, which is nothing but the rate of change of a property that you measure by sitting on a particle. So there's no motion, so the particles are not moving here, so they're equal. Now let's look at another example. Now this time you have a temperature gradient in the pool. So you have cold water here and you have hot water here. Now what's the physical reason behind the temperature gradient? We're not interested. Let's just assume that you have a temperature gradient, and if you take any point P, any fixed point, let's say F, and in space, you would not see any change in the temperature at that fixed point in space. So what that means is your dou theta by dou T is 0 this time. So what you're saying is that there is no, so at each and every point has reached a steady state. So there is no change in the temperature at any given point in space with time. It's a very, it's a very practical situation. There's no change in temperature at a given point, F in the pool. But there is a temperature gradient. So if you go from left to right, then you experience that the water becomes hotter gradually as you move towards the right of the pool. So, and remember that, and in this case, what we'll assume is that there is a velocity field, that is, there is a flow from left to right. So if you take a particle P and sit on the particle, and you start measuring the temperature change, what you will see is that as you move along in time from left to right with the particle, sitting on the particle, you will see that the temperature increases because there is a spatial temperature gradient in the pool. So my d theta by dt, which is the material derivative, which represents the rate of change of any quantity theta, in this case temperature, if I sit on a particle, in this case particle P. So this is positive, because as the particle goes from left to right, it gets hotter for some reason which we are not interested to understand or know the reason behind right now. Now the second term in this Eulerian description of material derivative was your v dot grad theta or since it's a 1D situation, so the dot product has no meaning, the vector has no meaning, and the gradient of theta simply is d theta by dx, where x is this coordinate. Well, let's call it y, because x we have been using extensively for material and spatial coordinates. Let's call this coordinate y. So the gradient is nothing but, the spatial gradient is nothing but d theta by dy. So what we see is that v, which is the velocity, is a positive quantity because the flow is happening from left to right in the positive direction of y. And similarly, d theta by dy is also a positive quantity because as you go to the right hand side, your theta increases, so the spatial gradient in theta is positive. Okay, and this is nothing but your d theta by dt. Again, remember, it's an intuitive understanding. You're trying to understand intuitively. Rigorous mathematical proofs will follow this discussion. Okay, so this is a situation where the convective rate of change completely contributes to the material derivative, and the local rate of change is 0. So I've shown you two situations, which are the two extremes. Of course, in a real situation in a pool, it may be happening that sun is heating the pool, and at the same time, the pool's also going from the temperature gradient in the pool. And if you sit on a particle, you see a change, which actually is a change because of the two quantities separately. So as you move to the right, you may also see an increase because of the radiative heating of the pool, which is heating the pool as a whole. Okay. So I hope that's clear. Any questions, please feel free to ask. Okay, so now we will see a rigorous mathematical proof of this. The material derivative being equal to the local rate of change plus the convective rate of change. So we will show this for a 1D situation. It's one-dimensional situation, but it will be quite straightforward to expand this to 2 or 3 dimensions in space. Okay, so I'll show it to you for 1D situation, and then you can easily show it for 2 or 3 dimensions. We'll say that let the description of motion is small x is a function of capital X in t. So you see that this time I'm not putting any vector signs because it's a 1D situation. So small x is simply one particular number. So small x denotes the Eulerian coordinate system, and capital X is the Lagrangian coordinate system. And then we have a property theta, which is theta as a function of either you write it as small x in t or you write it as capital X in t, depending on what description or what if it's an Eulerian description or a Lagrangian description. So we write the material derivative of theta with respect to time. So let's go to the definition of material derivative. So it was the rate of change of a quantity, theta in this case, for a given material particle or for a particle that you measure by sitting on a particle. So if you want to specify or fix a given particle, you specify or fix a capital X. Okay, so it's so this is how you define it. So you say limit delta t tend to 0, x at theta at x for a later time minus theta at x for a time t divided by that time change on a small time delta t. So that's the definition of material derivative from using your limits. Okay. So now we can write this term as or let's write that in words. So that's theta of particle x at time t plus delta t minus theta of particle x at time t divided by delta t, and in the limit that delta t is going to 0. Now this is a very important step. So theta of particle capital X at t plus delta t is nothing but theta of a spatial point small x plus delta x So what we are saying is that the theta of a particle capital X at t plus delta t time is same as theta at a spatial point small x plus delta x at a later time t plus delta t. So it's very important to understand that these two things are equal and these two things are okay. So at time t equal to t, the particle capital X was at point small x, and at a later time it's the same particle capital X, but that particle capital X has moved to the right, at a point small x plus delta x. So it, as the time changes, the particle is still the same, so capital X is still the same, but its position has changed to a point small x plus delta x. So using these ideas, I can write that theta, that's temperature at a point of a particle capital X at time t plus delta t, is the same as the temperature at a point small x plus delta x at time t plus delta t. Okay, so now if you understand this point, then moving ahead is very straightforward. So now we simply have to add and subtract terms. So we have added and subtracted theta at x comma t plus delta t. It's a mathematical addition and subtraction. Right. So we have separated the limits on two different ratios. So now we can easily see that the first of these terms is nothing but, so theta at small x plus delta x at t plus delta t minus theta at small x comma t plus delta t. So what I will do is I will multiply this by delta x and divide this by delta x, and then I can move around these terms. So I can just write delta t here and one of these delta x's here. So we can see that the first of these terms now this becomes is the partial derivative of theta with respect to x. Okay, so I've applied the limit as well here, and delta x by delta t, if you put the limit on delta t tending to 0, it becomes dx by dt. And then the second term is nothing but the partial derivative of theta with respect to t, the limit that delta t is tending to 0. Okay, so now we can see that this is the local rate of change, because remember that theta now is a function of small x and t. It's a local rate of change, and this is the convective rate of change. So dx by dt is nothing but the velocity. So that completes the proof of showing that material derivative, which is the rate of change of theta if you sit on a material particle capital X, is nothing but the sum of the local rate of change and the convective rate of change in the Lagrangian, in the Eulerian coordinate system. So that completes our discussion on material derivatives. Do we have any questions? Okay, if there's no question, then we will start with the next topic, which is deformation gradient. Right, so deformation gradient is very useful for us because it basically helps us understand what happens around a particular point P in a body. So I'll tell you what that what my statement means here. So let's draw the coordinate system. And then we have a body. So we'll have two different configurations here. So one's a configuration that we'll call the undeformed configuration. So we have, let's say, a physical body, which is initially at an undeformed configuration. And then we have a deformed configuration, which is the configuration that you get after doing some external loading on the body. And in this case, we are only considering two configurations. So we have one undeformed or the initial configuration and one deformed or the current configuration. So there's no effect of time here because we'll only analyze two configurations. One's the undeformed one and the other is the deformed one. And we're interested, remember that our interest is to understand what happens around a material point P. So let's say you have a point P and I want to understand what's happening around P. So if I understand, loosely speaking, if we understand what's happening around P, we understand, and if I have the information of what's happening around all the points in the undeformed configuration, I will exactly understand how my body is deforming. Okay. Speaking more clearly, let's take another point Q and draw a vector from P to Q. And since it's the reference or the undeformed configuration, we'll use the capital X for denoting this vector. Let me use a different color for more clarity. So this is D capital X vector. Now when the body deforms, what we'll notice is that our capital point P goes to point small p and the capital Q goes to small q. Okay, it's an exaggerated situation because that dx is supposed to be a small vector, but it looks quite huge. But again, as we said, that p and q are close to each other, but for drawing them on the board, we are using an exaggerated situation. So my point P goes to small p. So I can denote that using this vector. And if you remember what this vector was, this was nothing but the displacement u from point P to point small p. That's called the displacement vector. Okay, how a particle displaces from undeformed to deformed configuration. And this vector from small p to small q will denote as d small x vector. Right. So let's start the analysis. So we now before that, let's go back to the motivation here. So as I said, the interest is here to understand what's happening around a material point P. So what we'll do is we'll take all the possible vectors that I can draw at point P. That is, I move around my point Q in all possible ways, and then I see how capital PQ or how D capital X, starting with a particular D capital X, what kind of D small x do I get? Okay, so every D capital X will correspond to a D small x, and that D capital X going to D small x for all possible values of D capital X, that is, for all possible values of point Q around the point capital P, will give me the information about what's happening around point P. It will tell me how different points are moving around a given point, and that tells us how deformation is happening around a point, material point capital P. So the aim here is to be able to write d small x in terms of d capital X. So we'll see, I want to write my d small x vector as some function of d capital X. That's the aim here. All right, so let's start doing that. So I'll be writing my D capital X. Sorry, just to be clear, the vector is on capital X, okay, not on D. Okay, so D capital X here is written as D capital X A and E A vector. So E1, E2, and E3 are the unit vectors in the three directions. And then of course you have your small x1 or capital X1 direction. And you may notice that I've used a capital letter as an index here. But the reason we do that is, so if you have something written in terms of the material coordinates, we'll use a capital letter as the index. And if you have something written in the small or the Eulerian coordinates or the spatial coordinates, we'll have a small letter as the index. So I, J, K, etc. Okay, so it's purely for notation, nothing else. So capital A definitely goes from 1 to 3 in this case. And I'll write my D small x vector in the initial notation as D small xi ai. Okay, and the motion in this case is written as x I is a function of, well, there's no t here. We're just talking about two configurations, so we'll write it this way. So if you give me all values of, all components of capital X, I will tell you what the different components in small x are. So if you want to write in symbolic notation, what we're saying is small x vector, vector of a point small p here, is small x function of capital X. Just want to make things clear. So this vector is position vector of point small p, and this vector is the material coordinate or the position vector in the material or the undeformed coordinate system of capital point P. Okay, so starting using let's use indicial notation. So we can differentiate one with respect to A. So what we do is we differentiate the spatial coordinates with respect to the material coordinates. That's del small xi by del capital XA. So that gives us the second order tensor xi comma a, where I and a both go from 1 to 3 independently. And the reason we use this, and we'll call this as the tensor f. And why do we construct this tensor? So if I write my d small xi, this can be written as using chain rule. Since my xi was a function of the complete vector capital XA, so I can write a small change in xi as the rate of change of xi with respect to capital XA times dxa, where there's a summation implied on capital X. So this is using the chain rule here. So this now can be written as xi comma a dxa or fia dx, where fia is defined as the gradient of xi with respect to capital XA. Okay, so now you can see that the tensor calculus that we had learned, we are very easily or very comfortably applying that here without even expanding the terms. So this is the use of initial notation. That's the reason we got very comfortable with initial notation in the past few weeks. Okay, so if I write that again, so this is writing d small x vector as fia d capital X. In the symbolic notation, what I'm saying is d small x vector is the F matrix times d capital X vector. And this F matrix is called the deformation gradient tensor. It's an extremely important quantity. So if I just expand this F tensor, remember it was xi comma a, so which is del small x1 by del capital X1, del small x1 by del capital X2, and so on. So this is the deformation gradient tensor. So now you can see that if I give you the value of this deformation gradient tensor at a given point P, so let's go back and see what we're doing. So we were trying to calculate this deformation gradient at a point capital P, or for a capital point capital P. So if I give you the information about this deformation gradient tensor for this deformation from small x to capital X, or for the current situation that I have given to you, then you can write any vector around capital P in the undeformed configuration as the deformed configuration. So if it tells us what's happening to the points around capital P in this case, because you can understand what's happening around a point capital P by drawing different vectors around capital P and seeing how those vectors will change. If the vectors do not change at all, then that means that the body has not deformed at all. And you can also notice here that the information about translation is gone here, because all we measure is dx. So again, going back, if I say that the body is not deforming, what I'm saying is that my d capital X here in this situation is the same as d small x here. Well, it doesn't look like that here, but let us assume that it was the case. Then what you see is that the body has not deformed, but it has actually translated. But what's the different vectors may exactly be the same. So it's like taking a body and putting it somewhere else, then the information about translation is gone. But the information about rotation is still there. All the vectors would have rotated as a rigid body rotation. So that is something that you can see. But translation, in the information about translation is gone because you have taken a d, or a derivative of the motion. So we'll say that this quantity, it characterizes the local deformation at point P. Okay, so the reason we call it a local deformation is because we're talking about deformation at a given point P. Okay, now this quantity that you're seeing here, it may or may not be a function of capital X. Okay, what that means is that the deformation may either be non-homogeneous or homogeneous. So this F tensor can either be homogeneous. Homogeneous means that it's the same everywhere. So the value of whatever, I mean, if you calculate this and put numbers here, then the numbers will have no dependence on the spatial, on the capital X values. Okay, so it is homogeneous. The deformation is the same at each and every point in the body. So if you see that it's getting elongated, then it's getting elongated the same way in all directions. And non-homogeneous means that it has a dependence on capital X. That is, if you take different material points, they have different values of the deformation gradient tensor, or this tensor F. So this tells us if the deformation happening in a body is homogeneous or non-homogeneous. So now you can see that we are very confidently talking about deformation, and we are quantifying that in this case using the deformation gradient tensor. All right, so we will stop here today, and then in the next class I will continue from this point and show you what is the physical significance of this F, and how we can use it to define our strain tensor. Any questions before we stop?